All right, so I wanted to look at 3.2 with you, and you can think about 3.2 as just really two results that are telling you properties of the image and the preimage of a function, how they behave with regard to different set operations. The first of the two theorems is we're going to look at just two sets. The second of the two theorems generalizes these results as much as possible. So our setup, we're going to have x and y are sets. X is going to be the domain of our function f, y is going to be its codomain. And then it's important we keep track of where a and b live. A and b live in x, and then c and d live in y. All right, so we're just going to work through the statements here. I went ahead and wrote them down just to make this go a little faster. Hopefully it's not too horribly boring just to work through this list, but it's what we need to do. These are going to be important tools later on. So first off, the preimage breaks up nicely. It behaves nicely over union. So if you want to take the preimage of the union of two sets, it's just the preimage of the first union, the preimage of the second. How nice is that? And actually, a very similar result holds for intersections. The preimage of the intersection of two sets is the preimage of the first intersect the preimage of the second. You just can't ask for any better than that. That's about as good as it gets. And you might be thinking, oh, look, the image behaves nicely too. And it does for unions. So the image of the union of two sets is the same as the image of the first union, the image of the second, but not so with intersections. The image does not behave as nicely as the preimage when it comes to intersections. F of A intersect B is always contained in F of A intersect F of B, but the other containment may not hold. And so let's highlight that this one is not necessarily equals. It really is just contained in general. Next result says that the preimage behaves very nicely with respect to complements. The preimage of C complement is the same as the preimage of C complement. Super nice to know that. Finally, F of the preimage of C is contained in C, and A is always contained in the preimage of F of A. These need not be equal depending on your function F. They can be, but they need not be. And let's just look at F. Let's draw a little picture just for part F. Maybe here's your C, and here's the preimage of C. And certainly when you plug everything in the preimage in, you're going to land over here in C. There's no doubt that F of the preimage is contained in C. But you might not hit all of C. There could be some things in C, like over here, that don't ever get hit. And so that's why it's containment, not equals. So I don't want to prove all of these with you. I think that would not be very exciting. But I did want to prove at least one or two of these with you, just to show you how the proof goes, and also to show you that at least on the first, well, actually all of these, you don't necessarily have to do containment both ways. You can go carefully every step and realize that each step we're going to work out is going to be if and only if. And so it makes the proof a little faster. So let's prove part B, and maybe we'll do part E as well. So for part B, let's just realize that, look, X is in the preimage of C intersect D if and only if F of X is in C intersect D. That's what it means to be in the preimage. So that's clear enough. Well, F of X is in C intersect D if and only if F of X is in C and F of X is in D. That's what it means to be in the intersection. Okay, but that's true if and only if X is in the preimage of C, right? F of X is in C if and only if Fx is in the preimage of C and X is in the preimage of D. But if you're in both of those sets, then that happens if and only if X is in the preimage of C intersect the preimage of D. And so we should summarize this and say, thus, we've just shown that the preimage of C intersect D is equal to the preimage of C intersect the preimage of D. And I'm going to slide that down because I just don't like it looking like that. Okay, so that's part B. maybe we could prove part E as well. Let's do that real quick. So for part E, you know that x is in the preimage of C complement if and only if f of x is in C complement, right? That's clear. Well, that happens if and only if f of x is not in C. That's easy enough to see. And this happens if and only if x is not in the preimage of C. If f of x is not in C, if and only if x is not in the preimage of C, and that happens if and only if x is in the preimage of C complement. And so at this point we can say, thus, the preimage of C complement is the same as the preimage of C all complement. And so I'm not going to prove the others. They're all in the book, and I would encourage you to have a look at them. They go very nicely. Actually, it'd be a great way to go to sleep at night, is just to, before bedtime, pull your book out and work through a few of those. I think you'll sleep better, hopefully. All right, so let's stop this video here, and then in the next video we'll look at the other theorem, and maybe we'll prove one or two of those as well, and then we'll be done.